So, well, you've gotten my CV before you. Perhaps I could add that a footnote as introduction to the talk, that probably in the last 10 years, a large number of my colleagues, not the least Laurent, have tried their best to convert me into an infrared astronomer. And in fact, I spend most of my time, research time these days, when I can find research time, working on Herschel. But every once in a while, I have a relapse to my old ways of optical and ultraviolet astronomy. Since I know Maud Gallimay was here a few weeks ago to talk about Herschel, I thought I would talk about something that's not infrared for a change before I go back to Herschel probably in my next talk. What I want to talk about is an amalgam of several small projects that I've been working on over the last since I moved to Cambridge, basically 5 to 7, about 5 years ago. And it involves many students, current and former students and postdocs, including Ben Johnson, who is sitting in the audience. And the common theme between these is trying to understand star formation in the lowest surface density regimes, the lowest density extremes in galaxies. I'll set the stage with two plots that summarize much of what I know about star formation in galaxies. On the right is the relationship that you were referring to in my introduction, the Schmidt Law. In both of the axes of these diagrams, the vertical axis is a measure of star formation rate per unit area in galaxies, solar masses per year per kiloparsec. These are all logarithmic scales. So a measure of the intensity of star formation. On the right is this surface density is plotted as a function of mean surface density of gas. So this is the nonlinear Schmidt Law. On the left, the horizontal axis, the vertical axis is the same, but the horizontal axis is simply the absolute star formation rate in solar masses per year. So Milky Way on this diagram would sit about where my laser pointer is with a star formation rate of 2 or 3 solar masses a year. The lines here, in case you're curious, are diagonal lines are constant size of the star forming disk, 10 kiloparsecs, 1 kiloparsec, 100 parsecs. And then finally, to explain the color coding of the points, each point is an individual galaxy, either a normal galaxy or a central starburst in a galaxy. So the black points are normal disks like the Milky Way, and so this sort of sequence you see is basically the blue sequence, the now famous Sloan blue plume or blue sequence, but translated into a physical space of star formation properties. Then the colored points are various forms of starburst galaxies. The red are star-forming ultraluminous and luminous IRAS galaxies. Blue are blue compact galaxies identified in the optical or ultraviolet. The green are not so important today, but if you want to know, are the central circumnuclear starbursts, usually in barred galaxies, in the central kiloparsec of many of these normal galaxies. So if we focus on the left, the first thing, at least that strikes my eye, is the extraordinary diversity that one needs to try to explain of star formation properties. 7 orders of magnitude, 7 to 8 orders of magnitude in each axis. Of course, much of the variation in absolute rate is due to the fact that galaxies have an enormous dynamic range in mass. It's simply much of that range is just a mass scaling. But notice there is just as much dispersion in even the areal normalized star formation rate. And in fact, if I showed you a plot with the vertical axis being star formation rate per unit mass, or specific star formation rate rather than star formation rate per unit area, it would look very similar to this diagram and have nearly as much vertical variation. So there's enormous range in star formation activity, whether measured in an absolute sense or even a relative, a norm mass or areal normalized sense. The second thing that strikes me is the enormous variation in any one variable at a fixed value of the other. So even at a constant, say, a star formation rate of 1 solar mass a year, there is something like 5 orders, a factor of 100,000 variation in the intensity, or even more so if you go in the other direction. So a tremendous diversity. As one goes to higher redshifts, most of the galaxies, the famous Lyman break galaxies, BZK galaxies, submillimeter galaxies, if I were to plot them, would reside in the upper part of this diagram. It is not to say this part might not be occupied, but it's currently unobservable. It will remain for ALMA and ELTs and such to probe this regime at high redshift. So given that a tremendous diversity, it's all the more amazing that this 5 order of magnitude spread is reduced to about 1 order of magnitude if you simply plot instead of a single variable, the surface density of gas. It's simply confirming a few things, that baryon supply is the primary driver of cold baryons, or the primary driver, it's the concentration of that gas that matters as well, that is driving most of this dispersion. So that was sort of a 5-minute introduction, just sort of to the subject in general. And now to the subject of this talk, and basically for the rest of the talk, I'm going to focus on these two ranges. We're going to look at the very low surface density extreme. The high density extreme, the Eulerg starburst regime, of course, has been studied intensely for 20 years now and is a major focus of Herschel and will be of ALMA and so on. But data at the other extreme has been less, has come along more slowly, in part because of the difficulty observing galaxies in that regime. But I will argue today that understanding this regime down here is no less important for unraveling essentially the physical clues to what drives this star formation than working up in the more easy to study high density regimes. And if you ask what components of the galaxy population actually populate this physical regime, in fact, it's more than one. There are at least 4 separate environments in the local universe where you can study this sort of star formation. Probably the most widely publicized recently are the very outer disks of normal spirals. About 20 to 30% of spirals like the Milky Way actually have star formation extending 2 or 3 or 4 times further away than, say, the traditional divocular radius. And this is now often referred to now as XUV disks, as in extreme ultraviolet, because the Galax satellite has been a very powerful tool for revealing these regions. It's also a regime that is found in some early type galaxies, in particular S0, and occasionally even elliptical galaxies. It's been known for decades now, also the regime actually probably first pointed out in what are called low surface brightness galaxies, an example, Malin 1. And finally, it is much of the star formation in star-forming dwarf galaxies, very low-mass galaxies, also takes place in a very dispersed form at surface densities that also overlap with those illustrated in these other 3 regimes. And in today's talk, what I'll do for today's talk, after a little more introduction, is sort of take you through a quick review, sort of mini review of 5 to 10 minutes each on what we have learned recently in each of these regimes, and then I'll come back with some applications. Actually, I think I have a slide on that. So that's sort of the phenomenological introduction, and what will guide the talk are, I think, I've tried to pose at least 3 general questions that motivate. I've said that we have a great deal to learn from this regime. Well, what are examples of what we can learn? Well, the single most fundamental question I think you can ask about this regime, and it would be a question you could ask about starbursts at the other extreme as well, is the star formation we see in the extremes of the Schmidt Law, either end, is it really simply the same kind of, physically, the same kind of star formation we observe in Orion or W3 and so on, except with the star-forming regions packed together or dispersed. In the case of these galaxies, is it the same mode of star formation, just with the events more widely spaced? So it's nothing physical at all, it's just an artifact of surface density. Or when you disperse the star formation that widely, do you enter a distinct mode? Is there a different mode? And this, of course, those of you who work on starburst galaxies know they ask the same question there in the opposite sense. In particular, for example, does this change the initial mass function? Is the efficiency change in a dramatic way? Does the Schmidt Law break down? Does it apply there or not? We really don't know. And as I'll give examples in a minute, you can ask the question, I think a very important question, maybe the most interesting, is the key physical, let's say the condition of the many physical conditions that trigger star formation, is that controlling variable the same at low density as it is in higher density regimes? And I guess I've sort of just, that essentially is the second question. What can we learn about the physical factors controlling star formation by looking over a wide dynamic range in properties, comparing these regimes to those locally? And then number three is a rather general question, but I'll give you at least one example at the end of the talk of how we can apply this is, apart from using these dispersed star-forming regions to understand star formation itself, these regions, these clusters and H2 regions also provide us with signposts, essentially test particles that are probing galaxy evolution in regimes that are far removed, in the case of the XUV disks, say, at distances far greater from the center of the galaxy than could be studied previously. So one can use those regions to study, for example, chemical evolution, dynamical evolution, and so on in galaxies, again, in physical regimes that aren't very well studied today. So, so before I begin to try to address some of these questions, let me make a few remarks about this second bullet, just to give you an example that this is more than sort of a trivial, the questions here are of more than trivial importance. This is a slide I put together, I think, from a set of lectures I was giving last year on star formation. It was my attempt to list all of the steps. If you imagine beginning with a hydrogen atom in the intergalactic medium and then ending up in a star today, what are the steps that gas has to go through before it goes from essentially a member of the dominant baryonic component of the universe to a star today? And this is a grossly oversimplistic list, but already you notice it has, I think, 7 or 8 steps. The first step is, of course, that gas has to accrete from the cosmic web onto the galaxies. You might think that that is simply a different problem. That's cosmology, not star formation. But in fact, there are a number of papers that have numerical simulation papers that have come out in the last couple of years, which argue that in fact, the factor that drives the star formation rate of galaxies today is set by the rate at which essentially the cooling flows, the cold, whatever you want to call it, cold accretion or accretion of gas onto the galaxies is set. We don't know, I've put the question mark, whether it's fundamental or incidental, but it could be fundamental. Once that gas accretes, it has to settle into a neutral, essentially settle into the disk and obviously recombine into a neutral phase. Easy for disks, difficult in spheroids today. Once you have a neutral disk, eventually then several things need to happen, and here's where the theory becomes vague. In some order, and these may not be in the correct order in all galaxies, even today, you have to form bound clouds. Obviously, you have to have a gravitational instability take hold. That gas has to cool first to of the order of 100 degrees Kelvin in a cool atomic phase. That atomic gas then needs to form molecular gas or molecular clouds. And then, of course, from there, once the molecular cloud forms, as experts on star formation know, you have to make bound cores. That cloud has to fragment. form bound cores, and then those bound cores have to contract further with some efficiency to form stars and planetary systems. These study of these sort of, this regime is in the galactic studies, sort of out of the areas I study, at least today. But in fact, observations of nearby galaxies are critical in understanding the sequencing here. I think there was a time, maybe 10 or 20 years ago, when the modeling of this part of the critical middle part of the process was very simplistic and basically bundled all of these processes together with the idea that, for example, when I was interpreting star formation thresholds 20 years ago, I simply found that the features were explained nicely by gravitational, very crude instability models, Tourmalet instabilities. And it would seem the observations were consistent that if you form bound clouds, you would then form cool gas and molecular gas. There was really one cause, it was this, and the effect were these. However, there is a whole spate of literature, which I may very briefly touch on later in the talk, which argue in one paper or another that, in fact, what first happens is you form the cool neutral phase, the gas then cools, becomes denser, and then gravitational collapse and molecular formation follow. And there's a whole school of papers, many of them out of Berkeley, which argue that the only important, the critical step is this one. It doesn't matter as long as you can form molecular gas, that sets a chain of events in motion that lead to star formation. So much of the debate in the field right now in the sort of embryonic theory here is trying to understand how these things couple together. And I'll just mention one thing, quick thing is, I think adding to the confusion is that in the solar neighborhood, the pressures in the interstellar medium is at such a value that, in fact, most of these processes do occur at about the same column density. You can actually, in principle, there ought to be in galaxies physical regimes where you can have not only gravitationally bound molecular clouds, as we see in the Milky Way, and then the rest being in a diffuse non-bound form, but at higher pressures you could imagine having, breaking the degeneracy and having diffuse atomic gas and diffuse molecular gas before you had molecular clouds, or at low densities, gravitationally bound clouds. And we could put a third condition in here for a cooling instability. In principle, you can have most combinations of these regimes, but it just so happens that over much of our region of the Milky Way disk, we're at the crossing points of these instabilities, and so you tend to have two dominant media. One of the things that these low-density galaxies offer us, in principle, just as an example, is an opportunity to observe at much lower pressures and actually begin to break the degeneracies that drive some of these processes. An additional advantage is, although these four regimes are similar in that they all occupy this low surface density zone and star formation rate per unit area and low column density, in fact, they differ in many other properties. For example, in the dwarf galaxies, the metal abundances tend to be of an order of magnitude lower than in some of these other regimes. So you're able to hopefully be able, and so for example, metal abundance affects much more strongly the formation of a molecular phase, and it's, certainly it doesn't affect the gravitational instabilities at all. So I think over the long term, by studying these, not only the low density regime in general, but in fact the different types, it should be possible to unravel some of these competing factors. And it may well be that the critical path to star formation, say in the Milky Way, if it's in the Milky Way, it may be either the formation of a cool phase or a gravitational phase, that in fact, which of these three processes is the critical one that essentially is the physical cause for the others may change in these different environments. So I apologize for a rather long-winded introduction, but I think it will set the stage in going a little more quickly through the rest of the results now. So what I'd like to do now is very briefly give you a snippet of recent results sort of characterizing the star formation in these 4 different environments. So we'll begin with the early type galaxies. This is a subject I don't work in personally, but it fits into this general theme, so I'll give a very brief review there. The exemplar galaxy here is a fascinating one from a recent paper by David Thilker. It shows NGC 404, which is quite likely the nearest, I think, non-dwarf a spheroidal galaxy. It may be an S0 rather than elliptical in the local universe. In the optical, it's cataloged as a pure red and dead system, partly because I can't remember, one of these 2 stars is about 100 times brighter than the galaxy itself. It's a very bright foreground star, but it's a very red foreground star. So in the far ultraviolet, 155 nanometers, where this image was taken, the star fades away. And what is revealed is, in fact, that this nearby spheroidal galaxy actually has a very impressive disk of star-forming regions. We now know that star formation, while not necessarily ubiquitous in all early type galaxies, is much more common. Here I am somewhat embarrassed because I think there are people in the audience who have worked on this subject more than I, so I'll touch the highlights. Probably the best single slide to illustrate this is shown here. It's one of the, probably a real illustration of the impact of Galax on this field. What is shown are colors, 2 sets of colors for a sample of Sloan elliptical NS0 galaxies from a paper by Sugata-Kavaraj et al. The top panel are Sloan G-R colors of these galaxies, 2100 galaxies. And you see they form a very tight sequence in optical color. This is essentially the red sequence, often called the red and dead sequence. Were you only to rely on visible colors, you would have no clue, really, that these galaxies are, some of them are actively forming stars. However, if you use the color baseline that Galax provides, form a color index of NUV, about 230 nanometers, minus R, and plot the same galaxies, then you still have a red sequence up here. Most of these, what little UV is coming out of most of these galaxies is probably UV upturn emission from post-AGB stars and such. But then about 30% of the galaxies have strong ultraviolet emission that cannot be easily attributed to an upturned population. So it is believed, it was argued in the early Galax papers and in Sugata's papers that for about 30% of the ellipticals, they actually, this UV emission must be coming from young, massive stars. The absolute star formation rates are low, typically hundredths to tenths of a solar mass per year. And since these are very massive galaxies by and large, the fraction of stars being formed even in the last, say, 5 gigayears would be tiny. Again, probably less than 1%. So this is not like star formation in a spiral or starburst galaxy today, but it's finite and significant. I think many of you may have had the same reaction I did, that I did not find these data alone to be entirely convincing, but in fact, since that time, there is a very impressive confirmation, first from optical IFU surveys. These are just 2 examples, I think, for 4 galaxies. H-beta emission line maps from Sauron for 4 of these galaxies that show extended, in O3, extended star formation. Sometimes it's a nuclear disk, sometimes it's a circumnuclear, very often a circumnuclear star-forming disks, and sometimes much more extended. Francoise has led at least one, I think more than one, study of the molecular properties of first the Sauron galaxies and now the much larger Atlas 3D sample found, as you saw in the last slide, surprisingly high, a detection rate, again in the range of about 30% in single dish CO measurements, And now I believe there's follow-up measurements with Karma by the Atlas 3D team, and even hints of that they may fit on an extended Schmidt Law at low surface density. I won't dwell much more on the ellipticals, but except to say that that one of the revelations and a theme you're going to hear again and again in the talk is one of how ubiquitous star formation is in galaxies, that whenever you have significant concentrations of gas, it seems that nature finds a way, almost always, not quite every case, but very often, to form stars. It's much more prevalent in galaxies even today than had been thought before. The next regime I want to move over quickly to, and one that I've been involved with more directly, is extending the same sorts of studies, but now rather than to the left-hand end of the Hubble sequence, to the lowest mass range of the stellar populations. There have been a couple of, at least two big surveys, H-alpha surveys of galaxies in the local universe in the last few years. The one I've been involved with is the 11 megaparsec 11 Hug survey, and then something called the local volume legacy, an infrared follow-up. I'll just talk mainly about that. This was an effort to obtain H-alpha and then eventually ultraviolet and Spitzer imaging for a volume-limited sample of galaxies within 11 megaparsecs, so that we could have true volume-weighted statistics on star formation. When you observe every galaxy in a volume, of course, you mainly observe low-mass galaxies, dwarfs, just because of the shape of the luminosity function. And this is just a nice little picture, diagram that Janice Lee put together. It shows the histogram of star formation rates per unit mass as measured by the H-alpha equivalent width, with examples of galaxies in the local volume that fall in these categories. Staying on the theme of ubiquity, probably the first surprising result that came out of this survey came out of the detection rates of H-alpha and ultraviolet emission in these galaxies. There were about 450 galaxies in this 11 megaparsec survey, of which about a little more than 300, about 320 were dwarfs, where I think we defined dwarf as basically SMC mass or lower. And out of those, well, let's say 300, rounding off, we found H-alpha emission. Even though most of these were extremely low mass systems, we detected H2 regions in 200, well, let's say it wasn't exactly 300. If it were 300, all but 10, 290, had H2 regions, which meant they'd formed massive stars more than 15 solar masses in the last 3 or 4 million years. There were a few exceptions, and this is an example of the nearest of those. I think this is DDO 210, a galaxy at the outskirts of the local group, extremely faint, absolute magnitude -12, like that, or not too far from that of probably Omega Centauri, something, but an entire galaxy. This is an R-band image taken at the Bok telescope. Here is the H-alpha. It's deceptive. You see, unfortunately, this galaxy is in Sagittarius in the galactic plane, and everything you see here is an artifact of incomplete continuum removal of the stars. There are no detected H2 regions. We do detect a planetary nebula in the galaxy to prove, we had the filter tuned properly, but it is a complete non-detection in H-alpha. So this was an example of one of the 10, one of the 0.3% that don't have recent star formation. On the other hand, when this galaxy was imaged in the near and far ultraviolet with Galax, NUV here, far ultraviolet, you see it's full of star clusters. So it means that even though in this galaxy there's no star formation at this moment in the last 3 million years, over the last 50 to 100 million years, which is traced by Galax, there have been a number of star-forming events. And in fact, of the 10 galaxies not detected, 8 out of the 10, in fact, are like DDO 210. So, in fact, if you ask out of these 300 dwarfs in the local volume, how many have not formed stars, let's say in the last 100 million years, By the way, the selection was, they had to have H1 in them, basically. So of course, they have no gas in them, we didn't look. Only 2 are not detected in H alpha or UV, so of order 0.1%. So it really speaks to the fact that even down to the lowest masses that we can study, star formation finds a way in these objects. Then I'm going to move along a little more quickly so I don't run over time. The last regime, I'm going to talk next about star formation in the outskirts of normal spirals, and I'll also talk about the low surface brightness galaxies along the way, because they seem to be manifestations of pretty much the same phenomenology. This is an example of the poster child, the sort of object discovery of the outer ultraviolet disk of M83 that sort of triggered a whole set of follow-up studies. Here are images of M83 that you're used to seeing, showing sort of basically the divocalar diameter, both in the near ultraviolet, well, in the Galax, and in H alpha here. And that's the region you see in the center. However, with its 1 degree field of view, when Galax sat on this object for an hour, it discovered, of course, the star formation dispersed much further out. And I think this is from a publicity slide, press release. If you overlay contours of the 21 centimeter H1 emission from the Things survey, you find that, in fact, these blue knots nicely trace out and nearly go out as far as the H1 itself goes. This dispersed star formation was seen long before in H2 region surveys, going back to the work of Cortez and Paul Hodge in the 1970s and 80s. Annette Ferguson, myself, and others, there are catalogs that have shown isolated instances of star formation at quite large distances beyond the divocalar radius. However, it was Galax that really showed again the ubiquity of this phenomenon. Thilker estimates from another complete survey that among massive spirals, something like 30% have star formation extending well, say more than 50% beyond the divocalar radius. It's very interesting, among the 70% that do not, many of them also have very extended H1 envelopes. So this is not an example, how would you say? This is not the exception, it's quite common, but there are galaxies that behave very differently. We really don't understand that dichotomy right now. M83 is the more typical example where this XUV disk is simply an extension of a very intense inner star-forming disk. Now you ask how much of the total star formation in the galaxy is represented by this outer disk. It's actually, although it looks impressive, it's really less than 1% in this particular case. On the other hand, there are galaxies like NGC 1291, an H1-rich lenticular galaxy or SA galaxy, shown in H alpha here, and now next in Galax, where essentially the XUV disk represents all of the star formation. There are galaxies in which the gas supply has been completely used up within pretty much the divocalar radius, and they are pure XUV disk systems. And in fact, the low surface brightness systems like Malin 1 is an example of sort of the hybrid where you have a very low level of star formation following an exponential disk continuously from the center. When this class of galaxies was first discovered, a number of claims were made which I think exaggerated the effect. There were questions, for example, could this star formation make up half or 2/3 or 3/4 of the star formation in the universe? Do we have to adjust our Maddow diagrams to add this component? The answer is no. It's again few percent or less. There were claims that there was only UV emission out here and not H alpha emission. Therefore, the IMF had to be peculiar. Again, as I'll show you, that isn't the case either. Nevertheless, they're still fascinating systems. What has changed in the last couple, 3 years is that the advent of systematic studies of these galaxies. People are now making surveys of complete samples, getting multi-wavelength surveys of them. This has taken a long time because it's difficult. You have to get a lot of observing time to work out here. And again, I'll just give you examples of a couple of results about the star formation out there. This is a nice paper by Kristlein, Zritsky et al. From last year. They realized that a very sensitive way to study outer disks, not in ultraviolet, but H-alpha, was to study edge-on systems, where you can use the foreshortening effect to essentially get much stronger surface brightness sensitivity. And we need not look at the distinction between these three diagrams. If you look, here is a composite, a stacked radial profile of a set of edge-on galaxies. They're divided in interacting and non-interacting. This is, I think, the non-interacting set. And what you find is that, in fact, there is star formation extending well beyond the divocular radius, but there is a turnover. These galaxies do not have sharp edges at the divocular radius. The star formation continues. On the other hand, there usually is a fall-off, a rather steep fall-off in star formation rate corresponding near that radius. At Cambridge, we took a different approach. We took about 20 SINGS galaxies and obtained very deep H-alpha images going well beyond the divocular radius, and then compared those to the light profiles one sees in the ultraviolet. And what you find is a fascinating range of properties. In most of the galaxies, the star formation is traced by the most massive stars, and H-alpha actually very closely traces that by basically the B stars that you see in the far ultraviolet. So, for example, galaxies like NGC 925 show relatively little emission beyond the divocular radius. That's the yellow line in each case, and this is a logarithmic scale. So they tend to cut off completely, almost completely, not far out of R25, both in the ultraviolet and in H-alpha. Then there are galaxies where the UV emission extends at least twice, essentially nearly twice as far, or up to 4 times the divocular radius, but so do the H-alpha disks. They follow just as well. And then there's a subset of the subset of UV disks of maybe something like 20% of the galaxies with extended disks that have the phenomenon of UV emission that extends very far out. But in fact, the H-alpha disk truncates more dramatically. So this was, in the first few studies, this was thought to be the behavior of all of these systems. No, this is extremely rare, but these objects are fascinating, and we really don't understand what's going on here. It seems to be a change both in the number of resolved star-forming clusters, but also these galaxies often have a very diffuse UV emission at large distances, unusually so, suggesting maybe it's some sort of temporal phenomenon, but in any case. So I think the story that these objects were signposts of some sort of peculiar IMF in the outer disks is largely being debunked, and I'll come back to that in a bit. So that was sort of the overview of the sort of the review of the properties of these different classes of galaxies with low star formation rates. I now want to conclude the talk by quickly just going to the questions that I posed at the beginning of the talk and give you examples, 3 examples of how you can now take either the observations I've shown you or, say, follow-up spectroscopy of those regions to begin to learn useful things, either about the physics of star formation or the chemical evolution and so on. So the first application is a clear application you might think of is these extremely low surface densities allow you now to extend the study of the Schmidt Law to regimes that I was unable to probe in 1998 when the diagram at the beginning of the talk was published. So this has been done with a whole series of follow-up studies, and I'll give you a couple of examples of those. These 2 plots are from a paper published by Ted Wider and the Galaxies team a couple of years ago. And what they did is they used the combination of 21 centimeter mapping and Galax light luminosity profiles for a large set of these Malin-1 type low surface brightness spirals to ask the question of whether the global Schmidt law that some people call Schmidt-Kennicutt law extends, actually finally has a turnover at low density. This diagram is similar to the one at the beginning of the talk. Each point is the disk averaged star formation rate for a normal spiral, or normal spirals here, starbursts up here, and the colored points are a set of about a dozen low surface brightness objects where they were able to measure these quantities as well. And what you see is, in fact, for the first time, we actually see evidence that this global galaxy average Schmidt law does turn over due to the effects probably of star formation thresholds at low surface densities. On the right is a diagram derived from the same data set, but rather than plotting each galaxy as a single point, taking the average of the star formation rate per unit area and gas density across the whole disk, each line represents a radial profile in that galaxy. And you can see, likewise, even within each of those galaxies, you see it fall off in star formation rate and gas density with radius that is highly nonlinear. In other words, although both the gas density and the star formation rate are falling off, the star formation rate is falling off much faster than the gas density. So you really are finally entering this threshold regime in the low surface brightness galaxies. Now, that is not the first evidence of star formation rate thresholds in disks. This goes back to, well, my first work on this was 1989, and there were others who came before me. Here is a diagram from a paper by Martin and Kennicutt showing where the Schmidt law, integrated Schmidt law, Schmidt law for the inner disks of galaxies. Then when you do radial profiles even of normal disks, you reach a radius at which that turnover occurs near R25, where the density falls off. Now, we are guilty. This is a plot I wish we had not published. These extensions, of course, in these galaxies, we hit a radius in which we no longer saw a star formation, so we no longer could plot a surface density. So schematically, whenever we saw that cutoff, we made a vertical line, not realizing we have this log scale here. Of course, we're not making any measurements here. And this has led to confusion that we were saying there was no star formation outside R25, our own fault. Anyway, you can no longer, please do not cite this paper any longer, cite this one in these papers instead. This work now has been done properly using Galax, Spitzer, and 21 centimeter and CO data by the Things team. This particular diagram is from a recent paper by Frank Begiel et al. It shows the same kind of turnover in many of the same galaxies. And the additional interesting part of this figure is the colored, this is again a Schmidt law, the colored regions correspond to the regions inside of R25, so it's showing, maybe around R25, where you see the turnover in the star formation rate. And these are the regions way out in the XUV disks of M83 and I think a couple of other galaxies. And it shows that they continue that fall off. And it shows, in fact, there may even be an offset in these outer disks. So once again, although you can trace in the ultraviolet star formation as far as you can trace the H1, that's a bit of a misleading statement because what it's saying is that in those outer disks, the star formation is actually falling off quite a bit. Not only is the star formation falling off, but the star formation rate per unit gas mass, the efficiency, is strongly falling off out there. So in one of remember the first question I put up at the beginning, is star formation in these outer low density regions the same old star formation spread out? Well, at least in one respect, no. The global efficiency, the rate at which stars are being squeezed out, although the star formation continues at some level, the rate at which those stars are forming per unit gas mass is falling off quite drastically. So it in some sense has to be operating in a different regime physically than in the solar neighborhood. I think I'm going to have to skip through this because I want to show a few more results before the top of the hour, but just briefly say that one of the byproducts of the influx of observations on this problem, particularly in the lower density regime, has been to bring a lot of bright theorists back, into the field, trying to understand these phenomena. So, in fact, although the observations are beginning to converge on this, the interpretation is not. You can still explain these turnovers in efficiency by gravitational thresholds, but others would argue, for example, Upshai, is that, in fact, what we think we interpret as gravitational thresholds are actually driven by cooling instabilities in the ISM, that it's really a change in the phase of the ISM which then induces a gravitational instability. There are yet other, Krumholtz and collaborators have argued that, in fact, it's changes in the UV, essentially the self-shielding of the gas in the UV for manufacturing molecules and for the ionization balance of the gas that are important. And there are more complicated models, for example, work recently by Uvastreicher and collaborators that try to look at all of these mechanisms in a self-consistent way. And so I would say I'm not an expert in this subject. I would spend, if I had a little more time, I'd talk about them. But I think from my point of view, this is a very exciting time because the observations at last begin to have enough fidelity to them that they actually can test and provide targets for prediction for the theory in this area. Let me now very, very quickly give you two more examples of what you can do. This is really a forward-looking talk, arguing trying to get you excited about the future of the subject rather than its past. Probably the most widely publicized facet of this subject is a suggestion, I guess would you say a conjecture by Pavel Krupa, Flam Altenberg, and others that argue that as you disperse the star formation and particularly form environments where most of the star formation occurs in small star clusters, that you will truncate the maximum mass of the stellar IMF. And that, among other things, will have implications for how you interpret, say, H-alpha observations of galaxies in terms of star formation rates. Perhaps the strongest observational hint to come out in the last few years that would suggest there may be something to this model were observations of this kind. I just give one example, there have been others, by Janice Lee. This shows a comparison for those dwarf galaxies in the 11 megaparsec sample, the relationship between the ratio, if you measure the star formation rate using H-alpha and standard collaborations, and ultraviolet, corrected for dust, I believe, in both cases, in massive and then plot that as a function of the star formation rate itself. You could, of course, plot either H-alpha or UV here. She's done H-alpha. In galaxies with high star formation rates, mostly massive galaxies, these two sets of calibrations give you comparable star formation rates. No surprise, and we calibrated them against the same set of stellar population models. But the points, as shown by the points, as you go to dwarf galaxies with smaller star formation rates, going to 10 to the minus 4 solar masses and below, they tend to be systematically H-alpha weak. You get systems like DDO-210 essentially down here. And I believe the crosses are the fits to the data, and I believe the red is what the Krupa, one form of the Krupa-Flam-Altenberg model would predict. So, in fact, they have become very excited by this result, of which I'm a co-author, and I think Ben may be as well, suggesting that maybe they've interpreted this as evidence for a systematic depletion of the IMF. And notice this again as a logarithmic scale in the lowest density objects. Likewise, in other papers, they have argued that the same effect could produce the excess of ultraviolet emission, the properties of the extreme ultraviolet disks, that if, in fact, this IMF depopulation model is correct, you would predict that galaxies should have much smaller diameters in H alpha than the UV, that the outer disk should be primarily ultraviolet only. Well, the problem with that prediction is that, of course, I've already shown you it doesn't fit the models. There are a handful of galaxies like NGC 2841 where, in fact, the ultraviolet emission does trace out much more further than the H alpha, but this is the exception rather than a rule. Most of the galaxies, the massive stars and the intermediate mass, the 30 solar mass stars and the 8 solar mass stars seem to track each other quite faithfully at comparable surface densities of star formation. So at least in the XUV disks, I would argue that the Krupa model fails. More recently, this is from a paper about to be submitted by involves Dan Weiss, Ben Johnson, primarily, that I'm involved with as well. This question of the behavior of the H alpha and UV star formation rates in the dwarf galaxies has been reinvestigated, and with apologies for Ben for too quick of an explanation, what they've done is, these are the observations by Lee again as before, and they've constructed a series of models where they simply make the assumption, they drop the assumption that the star formation rate is continuous in time. They quantize the star formation into mini bursts with different properties, and they run a series of models with different histories. And what you find is, just by making the star formation bursty, which is confirmed by measurements of color magnitude diagrams with Hubble of these systems, you will produce this fall off naturally. Essentially, individual galaxies are cycling. When they burst, they go back onto the relation, and when the star formation switches off, the ultraviolet radiation remains, the stars remain brighter in the ultraviolet for longer. And so you can actually reproduce not only this fall off in this diagram, but also the relatively weaker trend in UV to H alpha to UV ratio with galaxy mass with these models. Whereas the Krupa model, although it does explain the Lee observations, in fact, predicts too large of a fall off in this ratio with galaxy mass. So I think the weight of now that the Krupa hypothesis is being scrutinized more carefully, it is being found to be wanting. That doesn't mean you can rule out a systematic IMF variation, but it's arguing that other factors are probably much more important, at least in these regimes. Finally, I will finish in about 3 minutes, I assure you here. The third application is just a teaser for the future, leaving the subject of star formation altogether, and give you an example of something you can learn that is completely different and new. And it is that since when we went back and got wide field, 1 degree field H alpha images of some of these galaxies with extreme UV disks, we discovered, in fact, that many of them had H2 regions in them. So, and that meant we could go back to an 8-meter telescope and take spectra of those regions, and we suddenly have a way to measure the abundance gradients and the radial abundance behaviors of galaxies to distances that are factors of a few larger in radius than we could ever probe before. And we are, with Fabio Breslin and Quentin Goddard and Emma Ryan Weber, we have now obtained spectra for a sample of 5 galaxies with XUV disks of different properties using a combination of the VLT and the Subaru telescopes. And this is an example from our pilot study, actually published a couple years ago now, M83. We used the FORS 2 spectrograph to measure about 40 H2 regions in these outer disks, plus a handful of objects in the inner disk, mainly with the idea of looking at the physical properties of the regions, the physical properties of spectra in terms of stellar population, but in particularly measuring the metal abundances. And well, that we can skip, just shows examples of the objects that we were able to probe. And I can summarize the results in a single plot. This is a plot of logarithmic oxygen abundance as a function of radius. Blue points are galaxies from the inner disk of M83, which we extended with FORS from work that Fabio had done. and then, of course, the outer disk regions here. Now, the lines are there to guide your eye. Perhaps we should not have cheated in that way, but the results we found were rather remarkable. What we found was that the points, the spectra in this inner disk here, fit the classical exponentially falling disk with an abundance of supersolar in the center, dropping to maybe 2/3 solar at the outer edge, but that when you go to this outer, XUV disk out here, a couple of things happened. First of all, the gradient became much shallower. You could argue almost flat within the errors, but still surprisingly metal rich, only at the minimum about 1/3 to 1/4 solar, even though the gas fractions out there we think are very high. And then I think a little less faithfully, evidence possibly of a discontinuity, two decoupled systems. I say possibly because those of you who know about H2 region spectra may know there are issues about the 0-point calibrations of these methods. But it appears that this outer disk may be a chemically decoupled system. Now, when we only had observations with M83, we tried to understand how could this happen, and it's easy for one galaxy to invoke a one-off, as the British would say, explanation. Maybe a merger, some peculiar event, some extremely rare event that would produce this. However, when we went to the second of the galaxies, NGC 4625, it's the second of the galaxies that define the XUV class or prototypes, we found the lightning struck twice, the same behavior of the outer disk having a significant drop in abundance, but then with a shallower gradient. Now, this is an interacting system. It has a companion about 10 diameters away, so again, maybe some accretion is involved. We have data we're still reducing from the VLT and Subaru on two other systems so far, and they show the same behavior of this turnover. So something very interesting is happening out there. We can't interpret it yet, in part because in order to test chemical evolution models, you need to know what the stellar mass densities are out there, how many stars are formed, the stellar masses of the outer disks, and they're so faint that we haven't found a wavelength, even Spitzer, where we can measure it out there. There are proposals by other teams to get deeper Spitzer images, to find out, but that's where it sits. So I'm over time by a few minutes, so I leave the motivating questions and ask, so what are the answers to the questions so far? Is this star formation regime the same or different than that we find locally? In between, definitely different behavior and star formation efficiency, but no evidence for a different IMF. Controlling physics may be different. And what does this reveal? Well, it's revealed that the chemical signatures reveal that explaining how those disks are there, how they form, why some galaxies have star formation rate out there, some don't, really is a question we can't answer, but they're intriguing hints that simple models will not work. So with apologies for running over, I stop there, and I hope I've piqued your interest in what should be a very exciting subject in the future. Thank you.